SQLAlchemy. Hi, I'm Mike. I am the creator of SQLAlchemy. Do I know people here, mailing list? Do people use the product or use the product? Who has no idea? I mean, the talk is kind of, I guess anyone could understand it, but it's maybe a little bit geared towards people that have used it. I don't know. I try to cover the bases. I don't really do a lot of talks. Anyway, thanks for allowing me to speak. And this is SQLAlchemy Architectural Retrospective. And there's a book that's out and called The Architecture of Open Source Applications. And I was asked to write a chapter for this book for the second edition. So this book is basically, each chapter is about some prominent open source project. I think like new Mailman's in there, and I think the OpenSSL might be in there. Other things. So I'm writing a chapter, and so when I did this this talk, I figured, well, let me kind of draw upon what I'm doing there. What I'm writing in the chapter has to do with where my thinking is at as far as the philosophy of SQLAlchemy's approach, and then kind of a rundown of kind of what are the high level things that SQLAlchemy does? How does it do it? And what I like about what I'm doing is that I'm trying to demystify it for people, because people are like, oh, SQLAlchemy is really big and scary, and it's really a tool set. It's really just a way to do things, and it's supposed to be it's best if you actually do know what it's doing and how it's doing it. It's best if you kind of just the same way you know how a screwdriver works. It makes it more useful. That was a really terrible analogy. Anyway, so I'm going to try to just read the slides now. SQLAlchemy is the database toolkit for Python. And it was introduced in 2005 with version 0.1, and today we're at version 0.7. It presents an end-to-end system for working with the Python database API. And very early, we had some early attention and success. Key features were fluent SQL, able to do lots of queries that other tools might not know how to do, and an object relational mapper that featured a unit of work pattern, which is a handy way to kind of handle persisting changes to the database in an automated way. All right, so part one of the talk is about philosophy, and then part two, I'm going to have some architectural highlights, and I don't know if I'll get through them all. I cut a lot of them out, so there's maybe 4 of them now, and we'll see how they go. So we start with the word abstraction, because when you deal with something like SQLAlchemy, we're like, okay, well, what is it? Oh, it's a database abstraction layer. So people have maybe differing ideas of what that means, or maybe my idea is different from other people. What do we mean when we say that a database layer is going to abstract something? So usually we might mean it's going to conceal details of how the data is stored, how it's queried. We just want to put our stuff in it, and abstraction layer will take care of it for us. Then where you start hitting a gray area, should it conceal that the database is relational? Should you be able to put stuff into it and query back, and you can change out, if it's a relational database, you can put a MongoDB behind it and it would be the same system. This kind of speaks to the question of how much of the back end should you expose. So SQLAlchemy, for those of you who know it, has taken a position on this, and it's really the one defining feature from the original release that kind of matched up with how I did things in the past, which was, here, this abstraction means hiding, in this definition. So the problems that we have with relational databases is when you work with a relational database, you're dealing with these objects that are, we have tables, we have views, we have select statements. They're called in relational algebra relations, meaning it's like a list of rows that have columns. So it's a grid, it's a tabular, obviously, structure. But when you work with a relational database, you're able to manipulate these structures together, and you can join them, you can put them on top of each other with unions. You can take any set of rows and then select from that. You can build on top. These are all relational algebra kind of things. And I think if you're using a relational database, these days you should be using it because you want to do things like that. If you don't, if you don't want to do things like that, there are other alternatives now. So if you hide those features of the database, then you really, why are you using a relational database? There used to be a time when you were building a web app, we need to store our data. Well, use MySQL, that's all there is. Now you have MongoDB everywhere. They have mugs, use MongoDB. If you don't need relational database, I'm here to say, don't use a relational database. Go use whatever you want. But if you do want relational database stuff, you should have a toolkit that's going to let you use it to the max, because you really should have all that available to you, while at the same time not losing the handy things that abstraction layers give you and object relational tools, I think, can give you. So we don't want to hide the database. We want to automate the work that we're doing with it. So I need the water. Okay, so automation, and this is a word I've been thinking about lately. It has to get to its own slide. So this means we're going to provide patterns to automate the usage of lower level systems. So like with DB API, we don't need to connect, then cursor execute, then do this less boilerplate. You can automate how you do things. Dealing with transactions is kind of handled. Dealing with differences in database quirks are often handled for you. So, and when you do your day-to-day coding, like you're running a query for some subsystem, you don't have to put too much there. There's a back end that's kind of handling all the nitty-gritty in a consistent way. So that's automation. Establish single points of behavioral variance. So if you wrote your application with a lot of hard-coded select statements everywhere, and then you change the name of a column, you've got to do a search and replace. Hey, Paul. You've got to do a search and replace everywhere. If you, on the other hand, have your queries coming from some kind of centralized metadata system, you can just change the name in one place. So that's single points of behavioral variance. You can also, swap out SQLite for Postgres. That's saying you just change one little string and you're on a different backend. So that's single points of behavioral variance, which you might not get if you hard-coded everything everywhere. When you use an automated approach, it doesn't mean you don't know what you're doing. It doesn't mean that, I just used SQLAlchemy and it wrote a bad query. No, you wrote the query, or you told SQLAlchemy to do the query that you asked it. You need to know what's going on, and it's even best if you know what SQLAlchemy is doing under the hood. The more you know, the better. And if you're trying to write something serious, you should go for demystifying things as much as possible. But when we work this way, it doesn't mean that we're having to just do the groundwork. I mean, the tool is still helpful. It's just that you know how it's doing things. We instruct our tools to do the groundwork we give them. And at all times, we're always going to decide what is happening. The tool is not going to decide what kind of tables we should have. It's not going to decide what kind of constraints we should have. It's not going to decide the names of things. We're going to make all those decisions up front. It doesn't necessarily mean we have to type it out 100 times. There's ways to automate these things, but the tool shouldn't do that. SQLAlchemy's approach is that the developer must consider the relational form of the target data. Query, as I just said, query and schema design decisions should be made by the developer. The tools shouldn't do that. The tools will provide a rich and detailed vocabulary to express these decisions. And then you should create patterns and conventions based on this vocabulary. And this is the part where SQLAlchemy, our philosophy might begin to diverge from what people are accustomed to, is that I think you should build something that's going to help use the tool in your way. So this is kind of the opposite of the approach of providing a coarse grain interface with defaults, everything, and then, if you want to use this kind of name, then change this default to be that instead. SQLAlchemy is going to work from the other way, where you don't really get too many defaults of any kind as far as your schema. You get a lot of components to build up a system where you then can express your conventions for your project or organization. So, about half the people have used SQLAlchemy and half have never used it at all. This is basically what a mapping looks like using the SQLAlchemy ORM. And if it's familiar to people, then you'd totally know it. And if it's not familiar, then I could quickly see what we're looking at. If you read our tutorial on our documentation, we kind of work a lot with this kind of boring example of the user and address table. And all user and address is just a basic one-to-many relationship. So say you have this application with a table of users, and then each user has 0 or more addresses, which On the tutorial, I think we use email addresses. For this example, I'm using street addresses. It's a contrived example. So when you make a mapping that's based on how the tutorial reads, you're building some classes that are your business objects, basically. And then when you use this style called declarative, you also put annotations on the class that describe how it should map to a database table. So it should be fairly apparent what you're seeing is that there's a table name which says what table should we be talking to, and there's a column called ID. A column object represents a column, obviously. There's data types here. There's a lot of detail about the data types. Some of that is optional. It depends on what you want to do with the schema. If you wanted to generate the schema from this, you'd want more detail. If you're using an existing schema, you would need less detail. But SQLAlchemy does want you to know, if you have a relationship between two objects, it does want you to tell it which column is the foreign key. So, one-to-many is like parent row has a primary key. The child rows have a foreign key relating. Does everyone know what I mean by a foreign key? Right? Okay. Good. So we're pretty verbose because we have a foreign key here, and then we also have this collection called addresses. So we're saying user has a collection of addresses, which is this address object, and then we also have to put that as a foreign key, and that is like people are like, why do I have to do all that? Because out of the box, SQLAlchemy is really looking for you to tell it exactly what the table looks like. And then as a separate concern, tell it how you want to map your objects to that table structure. So with the declarative style you see here, we combine those two levels of configuration together, which is not the only way you have to do it, but that's how most people work today. So we deal with this verbosity because it was some people would say it's too verbose. Well, is that verbosity a problem if the application is really small and just has 3 or 4 objects? And maybe this is arguable. I'm going to say that it's not. I'm going to say when we say, oh my God, that was verbose, I have 100 tables. I don't want to keep doing all that typing. I don't want to type ID equals column everywhere. SQLAlchemy is too verbose. So we have ways to deal with that. SQLAlchemy would say, well, if you have 100 tables, this is an application you're probably going to be dealing with for several months, if not years. Why don't you take a day or so and build a little bit of a foundation to automate the kinds of conventions you want to use? And the direction of SQLAlchemy lately with the ORM has been there's a lot more ways to build foundational elements to automate things than there used to be, and the declarative system really helps. So I'm going to go over 3 techniques that we have in our docs and I use in some actual apps I work on to kind of automate some of that verbosity. So one thing you can do, and this is all optional, this thing is that if you, like for example here we have a base class that will be the base of all of our declared mapped classes, and we are saying here that they all should automatically get a surrogate primary key called ID, and we're saying that they all should get a table name that's just derived from the name of the class. Now, some people might be like, I don't want an integer primary key. Well, this is your convention that you can change this to be what you want. This is your program. This is not us. We're just giving you the way that you can take the base class and change what's on it. You can also use a mix-in class, which is a class that's inserted into the middle of a hierarchy, to have some kind of convention in the middle. So if you want to have a certain subset of classes with certain kinds of conventions, you can put a mix-in, and I use mix-ins all over the place. So this is one convention. We've now made it such that we don't have to declare a table name or a surrogate primary key column for this particular example. Another thing we can do is, well, we have foreign keys. We know the foreign keys all want to be named table name underscore ID, and we know that primary key is always going to be called ID, so why don't we make a function that does that for us, so we don't have to keep typing out column, table name, integer, foreign key. We just have the FK def and give it a table name, and that's the last time we have to type out column, foreign key, because all of our foreign keys obey that pattern. If some of our foreign keys didn't obey that pattern, then you can type out foreign key, but for most of them, it's about getting 80% of the repetition out. There's always going to be special cases, but at least we don't have to do that thing all over the place. This is a more elaborate automation, and there's some examples on the site. We want to have a lot of different tables. Suppose we had a user table and like a customers table and like an employees table, and suppose they all had their own little addresses table with little street addresses, and that might not be the design that we want to use, but let's suppose that we did. There's probably better examples of systems where there's some kind of little related table that's repeated. We can make a little prototype for that table, and this is like a little cookie cutter system that will give us a table with those 4 columns whenever we need one. And then we can make a mix-in that we can apply to any class, like a user can implement the has addresses mix-in, which will use our address prototype. And there's some Python stuff happening here where we're basically using the type function to create a new subclass where the bases are our declarative base and the address prototype. And we use our little foreign key function to give it a foreign key back to the parent, and then we return a relationship. This is a little more dense, but there's a lot of examples of this with the SQLAlchemy distro and on the wiki. Does this make sense, or is this totally bizarre? Somewhat. It's okay. Okay. So I didn't know because I'm being in class on the fly, But this is not like the date. This is part of your foundation. This is part of the first couple of days that you're just writing up your patterns. You'd have this library called utils or something like that, or base, and then your day-to-day programmers don't have to do this kind of coding. This is just to set up your foundation. Day-to-day people would just be doing this. They would just be using the has address mix-in. So the mapping I showed you earlier that had all that verbosity, this is the exact same thing. And this is an extreme example, of course, but this is just 3 lines. So the point of this is just to show that it is possible to really decrease that verbosity. If you have patterns, you should set them up. So really a lot of the SQLAlchemy's configurational layers really belong in kind of this foundation where you set up your patterns and then you can come up with something really succinct. So this is the exact same setup. So unfortunately, my computer's not showing me the time. So, okay, 2023, which means I went too long. More foundation. Yeah. Okay, and I have this one too. So I went too long. So more foundation is available. I have a blog post. I'll put these slides up somewhere so you can click on the links. So there's more. Let me go through this one a little more quickly because I was hoping to do 20 minutes for that first part, and I talked way more than I thought I would. Exposing relational context. So when I mentioned SQLAlchemy wants to really expose how is organized and those concepts are exposed, it doesn't try to hide that it is. It's like power steering for SQL. The developer should be aware of the SQL, and you should really be logging. When you first develop, you should know what it's doing. It shouldn't be a mystery. Just like your car's windows, so you can see where you're going. This is kind of an example. So suppose we had some hypothetical back-end agnostic system that could talk to MongoDB, and it could also talk to Cassandra, and it could also talk to a relational database. If you were to ask it, okay, give me users where their address has a street called Green Street, and they don't have any addresses in New York, this is a non-controversial query, and it pretty much is going to generate a SQL query like this one. We have a join and we have an exist, but up in our query up there, we didn't say that at all. We just said, hey, just give me addresses, and the join is implicit, the exist is implicit, because it's not very controversial. So that's not a big deal. But then if you wanted to do a query with this user addresses structure, which is give me all the households in New York with exactly 2 occupants where neither occupant has any residences outside of the city, you probably could not use that system so easily to do this, because when you do this kind of query, you need to be thinking about the relational structures that are in place and how they join together, because this query is not really, our model really doesn't work very, very well with this query. Again, it's a little bit of a contrived example, but in the real world, you're going to have queries, that you're going to need to do that aren't going to work, beautifully with your model. Or you might have a system that has such a wide variety of kinds of queries that you just can't have a model that's going to suit them all. You're going to have some queries that are a little more elaborate, or you might have ad hoc reporting needs that have a more elaborate query. When you build this kind of query, let's say, suppose we were like a DBA, and we were just sitting at our Oracle terminal. We build this query from the inside out. We would get first. This is just one way to do it. If there's another way, that feel free to email me. Your way sucked. Let's get street, city, zip combinations that have exactly 2 user IDs living there. We're going to use the count function to count how many users, and having element filters on a certain aggregate value. That's one component of our query. Another component is pairs of user objects. So we're going to get pairs where they're not the same and they're unique. And then we can put them together. I'm going to go through a little quicker. So we're going to put them together here, and we line up on their addresses, and then we have to line up the address rows matching up the street, city, zips together. So it's a big query, and then we want to add the not exist any addresses in New York. It's kind of a big query, but we started from 2 little components and built our way outwards. And when you work with relational databases, at least in my experience, that's how you think about queries. Is you start from the small components and you build outwards. SQLAlchemy, their query object, because it is explicitly relational, you build it the same way, and then once you have the query, you can do more with it. So I'll just run really quick through what that looks like. Same component, the streets, city, zip combinations, in the same way, has the same kind of, it reads the same way, at least to me it does, has group by having, it's the same kind of thing. There's our 2 users, the pairs of users coming together. Here's how we join them together. Again, it looks different from SQL, but it really reads the same way. It's the join to addresses. It's got the same components, just in Python. And then we throw on the exist at the end. And then for kicks, we can also ask it to load the address collections. I mean, I wouldn't do this because it would be too many joins, but just to show that SQLAlchemy can automate adding on a join to the address tables as well, you get this query, which is crazy. But it's the same query as what we had before with some extra left outer joins. And then so we're basically automated having to dump this out. And if we were using any quirky things that change on backends, like those question marks might be on DB, they change. So we have this query that we dumped out, and we get a result. And the SQLAlchemy did a lot of work when we do this. It's actually going to take the rows and marshal them into our objects. So, that's what you can do with the ORM. Now, what some people say is that's leaky abstraction, meaning the abstraction is leaking the fact that there's a relational database. And yeah, so it is. So kind of sue me. Here's a quote from Joel: "All non-trivial abstractions to some degree are leaky." SQLAlchemy. This is the one thing that I knew I was going to do when I first wrote this, was that it just has to. It's just how it is. You need to know that there's a relational database, and you don't have to, but if you really want to work with the database, it needs to be exposed. So the goal is just being able to automate things, reducing boilerplate, succinct patterns of usage, less code, writing better code, but it's not, don't make me understand things. It doesn't mean that your application is not going to abstract away that there's a database in use, but SQLAlchemy is not the place where the database is hidden. You hide the database above the SQL. You build your own. So you take SQLAlchemy and your database, you build an interactive layer in your application, which is that foundation. Then on top, you present your app. So it's more work, but it's more about what I sometimes call handwritten code. So that's part 1. Was there any questions on that, or we'll just go through some architectural highlights? Is
it possible to build a mapping that's only partial? So
partial mean like only some of the columns? Yeah, you can exclude columns. The mapper has an include columns thing that can only pull in those columns you tell it, or an exclude columns that will exclude what you want. Yeah, there's other ways to not have to load those columns either. So the architectural overview, this is more closely following what the chapter I'm writing for, and there's many areas to the chapter, and I have maybe 4 things here, because based on how long I talk about things, I'm probably not going to get through these. So the first thing you deal with SQLAlchemy is what we call the core ORM dichotomy. So SQLAlchemy has 2 distinct areas, which are the core and the object relational mapper. And this picture is on our documentation, so this shows where the ORM is in relation to the core. So you see the core has got various components. We'll go over them in a second. So first, let's talk about what the core does. The core handles all database API interaction. It has a schema description system, which is a way to describe the tables and columns and other things that are in your database. SQL expression system is a way to build queries against those schema elements that you've defined. And the core, you can build your whole app using just the core. You don't need to use the ORM with SQLAlchemy. I have this all over the site because people are like, ORMs suck. Great. Well, you can still use SQLAlchemy because you don't have to use the ORM. A core-oriented application is schema-centric, and Reddit, the website, uses SQLAlchemy, only the core, and their site basically talks to PostgreSQL using SQLAlchemy core, select constructs, inserts, and the engine. The ORM, in contrast, is built on top of the core and knows nothing about the database API, the Python DB API. It maps classes that you create in terms of the table data defined with the table metadata is defined with core constructs. The ORM maps those to user-defined classes. It maintains objects in memory, your objects that you've defined, links them to a transaction, and passes changes on those objects back to the database, and also pulls in information from the transaction into your objects. It uses the core to generate queries, and an ORM-oriented application is domain model-centric. So what are the pros to this approach? The ORM doesn't need to know about how SQL is rendered. Doesn't need to know about the DB API. We can have people help us with our DB API and SQL rendering kind of things without really having to worry about what the ORM does. The ORM is highly integrated with the core, so if you're working with the ORM, you can still use core concepts. And early on, people, when the ORM didn't do much, they dealt a lot with the core because the core kind of exposes itself through the ORM. So they could still do whatever queries they wanted with the core, and they could still use the ORM for what it was providing at that point. And these days, when you work with the ORM, you don't nearly need to drop down to the core almost at all these days. What are the cons to this approach? New users need to be aware of the separation, and a big win for us was coming up with the name core. Historically, SQLAlchemy was like the SQLAlchemy ORM, and the SQLAlchemy, this is not the ORM. So we've decided to give it a name core, and that helped a lot. The core-ORM dichotomy is a performance hit, especially in C Python, because there's deeper call stacks. ORM has to call into the core, which calls into the DB API. If your ORM called directly to the DB API, you'd have a more shallow call stack. And C Python is very expensive with function method calls. PyPy hopes to improve this. It uses a JIT to flatten out deep call stacks into shallower call stacks, and SQLAlchemy runs with PyPy. And Alex Gaynor, who works heavily with PyPy, hangs out in our development channel, which is great, and he runs his own PyPy DB APIs against SQLAlchemy's test suite constantly. So we have PyPy going on, and hopefully if PyPy catches fire some more, SQLAlchemy is there. Selected architectural highlights of the core and the ORM. So the first thing we start with is taming the DB API. And why do we have to tame it? DB API is PEP 249. It's the spec that most of the Python client libraries conform to. The spec itself has got a lot of open-ended stuff going on. It's got a lot of undefined suggestions, guidelines. So as a result, dealing with DB APIs has a really wide variety of behaviors that we've had to normalize. There's many behaviors, more than I would say are reasonable, but especially Unicode is a nightmare. Numeric values, getting precision numerics, we've got to do all kinds of different hoops and extensions and plugins to get, like CX Oracle, for example, to return precision numerics without floating point errors. Lots of that stuff. So what is the system that we use to handle this variety? Well, we'll start with what the lowest level of SQLAlchemy that one person usually uses is the engine. So when you create an engine, you give it a URL like that. We're going to deal with Postgres and PsychoPG2 as our example. You can make a connection to the engine, which represents a connection to the database. We run a statement, and we get some results. Now, this is a facade over the DB API, which is a little more fine-grained and also less featured. So there's a lot of features here that I don't have time to do, but there's a lot that you can do with this result that you couldn't do with the DB API cursor. And you can also, there's a lot more that the execute can do that I'm not showing you. But first, we'll show what the architecture of the engine connection result is. So when you deal with SQLAlchemy engine, you're dealing with the left side, engine connection and result proxy. And when you deal with PsychoPG2's DB API, you deal with the DB API, the connection, and the cursor. In the middle of that are an object called the dialect and the execution context. And those objects handle variances in DB API module and connections. And the execution context is kind of a precursor object. So when you use PsychoPG2 with SQLAlchemy, you're actually dealing with this kind of hierarchy where we have two levels of variance in the database side of things, where we have the PG dialect that handles the things that are unique to Postgres as a database. Then we have a further subclass called PsychoPG2, PG dialect, which handles variances in specific to PsychoPG2. There's also PG dialect underscore PG 8000. So this two levels of variance idea we introduced in 0.6. Before that, we used to have just the Postgres dialect, the MySQL dialect, the Oracle dialect. It would just hard code to one DB API. When we wanted to support multiple DB APIs, we had to break it out into two levels. For a case like ODBC, PyODBC, which is a DB API that can work with multiple backends, or ZXJDBC, MXODBC, we mix in a package called connectors. And here, this illustrates how the PyODBC connector is shared by MySQL's PyODBC dialect and Microsoft SQL Server's PyODBC dialect. So that's a little bit of that. The DB, that's where we kind of, so this is how we package up the variants in DB APIs from a class construction level. SQL expression constructs, that was the first architectural highlight. This is the second one. Okay. So it wasn't clear in the early days how, when I was doing this thing, how SQL expressions should be constructed. I didn't know, because I came from a Java background mostly. I was kind of thinking kind of Java-esquely. Should we do like hibernate query language? Hibernate something like this, which is pretty horrific, but that was how we did things back in the day. I didn't really... okay, so actually I found SQLAlchemy, written by Ian Bicking, who is brilliant, and he had this really great idea that was like the light bulb moment for me. I was like, I'm going to do that. So what SQLAlchemy does, it has this package called SQL Builder, which is their expression package. This concept of Python objects that represent an element of a SQL statement, meaning when you see test1.q.call1, anytime that object is referenced, it refers to the same query. And if you had an alias of test1, you'd have a different call1 object that would refer to one alias. And it's really, the idea is that Python identity is used to identify a component of a statement, the identity of the call1 object, rather than a string. Instead of saying order by string call1, you have this object that enables you to have, the names no longer matter. It's their lexical significance in the statement. And then he's also using Python equals operator to produce a SQL expression. And how does that work? So if you work in SQLAlchemy or whatever, you have, say you had some column, you equate it to 2, we override the EQ, Python function so that when you say column A equals 2, the Python interpreter invokes the EQ, and you actually get this object called a binary expression, which later can become a string. So this is when you write your own, object relational layer. Anyone wants to go out and write your own SQL expression system, if you want to do the equals thing, it's going to look like this, where you hit those operators and produce some kind of object that you later can make a string. So a SQL expression, if we want to do select ID from user, we import the select function. We pass it some table metadata, which there was a slide that illustrated that before, but it's not there now because I took it out. So say we had a table object called user. User's got a column on it called ID, so you'd say select ID.where username equals ed. When you have this select object, it actually is going to create this kind of structure. So when I want to make a string out of this, you start with the select, and that's select, and then you go to the column. You basically traverse a column clause ID from user table. And then you go to the where clause where, and then you go name equals ed. So that's how, using hand signals, how a string statement is generated. And that's all the time I had for the core, because I cut out a lot of the slides. So the table construct I just mentioned before looks like this. So this is the intro to mapping. Am I going too fast? Getting information? Fine. Okay, great. So only the hardcore people show up at 10 a.m. It's good. So what the table, the metadata, the table description system looks like this. You have this object called a table, and this is a core construct. So when you use the core and you want to define the columns in your table, you say user equals table. You give it a name. It's owned by a collection called metadata, which is just a collection. And then you define everything about the table, and you can create table statements from this. You can do all that stuff. And when you use the ORM in original SQLAlchemy, you would first start with this core construct that lives in Python and describes your tables, totally agnostically of the ORM. And then you create a class, like your user class, and you create your address class. And then you use a function called mapper, which would say, hey, take the user class and map it to the user table. Take the address class and map it to the address table. And then also make a relationship. So this was our original approach, which is kind of hardcore. That's like your table definition should be there, your business object should be here, and never shall the twain meet. And this is still, something you can do with SQLAlchemy today. As you can read in enormous letters, the strict separation of database metadata linked by the also separate mapper step, we now call classical mapping. And if you read our docs today, we'll see this term classical mapping referring to, I'm hardcore, I want my tables over here, I want my classes here, and they're separate. So we don't stress this style as much now because I don't use it myself. It's just really overkill. And it's a lot easier to use the declarative system, which is where we showed before. You have these classes where you kind of embed information about the table at the same time. And if you look at most other object relational things that I've seen in Python and even in Java, Hibernate has annotations now. This is kind of more the approach you see today, which is where here's a class and we can just put little annotations. Here's how they map to the table. It's not that big a deal. You can also have a kind of a middle-of-the-road approach where we're going to map user, and because it extends from base, it'll automatically be a mapped class, but we can still have the separate user table on. We can have it inline. My current project does it this way, where we have the table kind of at the top. So it's kind of separate, but it's still in the same place, and we still have all the nice features that declarative gives you at the configurational layer. But all of these systems have in common is that they're all exactly the same. They all have the same end result, which is that there's a mapper object. You can get it for your class. Whether or not declarative was used does not matter. I see a lot of questions like, oh, but can I do that with declarative? Like, yes, it's the same thing. Nothing changes. So that's why I'm making this point, because not everyone seems to get declarative is on top of the mapper. It just is like configurational sugar, same thing. That's all it is. And also, when you say user.username equals some column, once the mapper gets its hands on the class, that column is replaced by this thing called instrumented attribute. So when you deal with your mapped object in SQLAlchemy and you're saying like, my user equals user.name equals John, you're dealing with this object called an instrumented attribute, which is actually a Python descriptor. Do you know what descriptors are, everyone? No? Descriptor is a Python object that intercepts set and get operations on both the class as well as the instance. And we use those really heavily. The architecture of when you map a class, this is what's actually happening. Your class is on the left side there, and your table metadata is on the right side. The mapper kind of knows about how your table links to your class through this instrumentation object called the class manager. And what we mean by instrumentation is we're taking your class and we're going to patch on attributes. It is monkey patching, but the word instrumentation to me suggests more of organized, formalized monkey patching. So it's not quite the same as monkey patching, which is just to solve a problem. Instrumentation is kind of like a formal system of monkey patching. And most ORMs are going to do some kind of instrumentation. Even Hibernate will annotate. You will change your bytecode. So between the table and your sum classes, the mapper has a collection of column properties. Each column property object maintains a column on behalf of an attribute, and each relationship property maintains another mapper on behalf of an attribute. So this is kind of, when you have your mapping, this is what's actually there behind the scenes. And the little boxes on the inside, they're in the book chapter if you want to see what they do. So that's what a mapping looks like. Fun facts about declarative. So a SQL object like declarative layer was always planned since the beginning, since now I've spilled the beans that I was ripping off SQL object. So I always wanted there to be a declarative system, but I figured I wanted to work on the mappings first because I was getting kind of sidetracked by having to work at this configurational system. And then early on, we had something called active mapper, which was kind of like declarative. It didn't work very well. And then Elixir was kind of active mapper taken out to its own thing. And Elixir lives on today. Elixir kind of heavily redefines the semantics of how things are mapped. It kind of looks like Ruby on Rails, active record. It has abstracted concepts like has, many. And it has that behavior where everything is something by default. And then if you want to change it, you have to change it. So it's kind of the opposite. Even though it uses SQLAlchemy, which is great, it's the opposite philosophy to what I'm talking about these days. So declarative is the other way around. It was introduced as a one-click away from classical mapping system, retains the standard SQLAlchemy constructs, just rearranging how they're combined. And this is me. I had to be convinced by Chris Withers to support mix-ins with declarative because I was like, those are never going to work. They're never going to work. And he implemented them, and I said, like, fine, put them in. And then I use them like a drunken sailor now, declarative mix-ins. They're, like, amazing. And those patterns I showed you, I really didn't put together how useful they would be to automate a lot of boilerplate. So the last section, because I have good five. Well, time is good, right? I guess my watch is fast. Okay, I have 5 minutes. Great. So there was a lot of different areas I could talk about, and I figured when I did these slides, the unit of work kind of came out as the most interesting thing. Like I had a little thing, how does the query work, and I don't think it would make any sense without really more detail. This will be a little overview of what the unit of work is and kind of what it does at a theoretical level. The unit of work's job is to find all the pending data changes in a particular session and emit them to the database. So, and a session is this in-memory holding zone. It's like this object that's got all of our mapped up. So we say, give us a new session. I'll show you an example in a second of what a session is. The unit of work figures out what's changed about your data and creates commands which emit batches of insert, update, and delete statements. Those batches, in turn, have to be organized such that dependent statements execute after the dependencies. And then in between those blocks, again with the hand graphical system, data is synchronized from the result of a completed statement, a statement that's already executed, into the parameter list of another statement yet to be executed. So what we're talking about here is, user rows are inserted, and then typically we're using some kind of increment feature, which means that when you insert a row, you get the primary key only when you do the insert. Particularly MySQL and SQLite have that behavior. So we don't know the primary key until we do the insert. So we do the insert first, get the primary key, and shove it into the address foreign key. So unit of work's got to kind of figure out new primary keys into future foreign key values, because we don't want to have we don't want to update things later. We want to have just this big line of inserts that does everything at once, so that they have to be ordered in a certain way. Not to mention that you couldn't insert the address rows before the user rows because of referential integrity. Even if you had the primary keys, the foreign key constraints would fire off unless you've used deferred constraints, which we don't assume because that's kind of an exotic use case. Too much talking. Okay, so an example of using the unit of work, we'd have a session, which is our holding zone. It's our main thing that we deal with when we use the ORM. We bind it to some engine that's going to talk to a database. We create some user objects. We have some address objects from somewhere. We throw them in a session. The session adds everything it needs. It knows about all the pending data, and then we can force it, if we want, to flush, which will emit SQL that looks something like this. We'll have two insert statements for user rows. Put the ed row in, put the jack row in. And then at the bottom, we'll see it's actually batching the insert for the address rows into a single statement. This is called in DB API an execute many. You send the statement once with a list of parameters, and the implementation can then optimize the insertion of many parameter sets, usually using a prepared statement or whatever the backend provides it. So DB API gives you a fairly coarse-grained way to get at that. We can batch statements if we already know the primary key ahead of time. The only reason that we can't batch inserts usually is because we need to get the primary key from an auto increment kind of thing. If we have the primary key, we can batch. So this is the unit of work. For that flush, would maybe do something like this. You'd see this kind of statement. So how does it do that? It has to sort things on dependency using this concept called the topological sort. And I learned that word when I read Fowler's Patterns of Enterprise Architecture. I was like, oh, a topological sort. Let me look that up on Wikipedia. That's how the unit of work was born. So in this sort, an ordering is produced which is compatible with what's called a partial ordering. And a partial ordering is pairs of values that indicate one value that has to come before the other. So this is a topological sort. If we have four objects, A, B, C, and D, and we have a partial ordering, which tells us about the rules for how they have to be ordered, A becomes before C, B comes before C, and A becomes before D. There's many possible ways to topologically sort those. So what these all have in common are those three criteria. So the result of a topological sort is not deterministic. It could be many things, and that is one reason why the unit of work can be very hard to debug, because based on Python ordering capriciousness, you might have the bug, or the bug goes away. And I've learned all about how to trick Python into, well, actually these days we just randomize the order of sets and hashes, and we run the test 5 times, and it'll hit the bug when we have those bugs. They're not that common nowadays, but I know all about, like, if you have standard output turned on, the bug will happen. If they turn standard output off, then the bug doesn't happen. All kinds of things like that. So how does the unit of work use this topological sorting algorithm? It has something called the dependency graph. So it sees all the mapper objects. So say you're going to flush users and addresses, 2 mappers. The 2 mapper objects represent nodes, and the relationship between them represents an edge. So for each edge, the mapper on the right is considered to be dependent on the mapper on the left. meaning one mapper is dominant over the other one as far as who gets inserted first. And when you do deletions, it's the opposite. The addresses need to be deleted first, then the users. A dependency usually corresponds to mapper B's table having a foreign key to that of mapper A. And these pairs of mapper objects form the partial ordering. So user and address related by user.addresses would be, this is the partial ordering, and the tuple syntax is because that's how we represent them internally. We'll have a tuple with the user mapper, and the address mapper. And the user addresses relationship is what generated that tuple when we first do the unit of work. So when we flush user and address in this simple, this is the simple case, we a series like this where first there's a bucket of all the users called save update all. So we do all the inserts for all the users. Then we have a bucket called process all where we copy all the primary keys to foreign keys. And then we have a bucket called address save update all for addresses. We insert all the addresses. And this is very simple. And also it scales. If we had 10,000 users and 10,000 addresses, we still have just 3 buckets with 10,000 users, 10,000 objects each. So the reason we do this per mapper sort, which actually doesn't work in all cases, is because it's efficient. In the case that we have a simple relationship of mappers, we can do a very simple kind of flush. Now what happens is you get cycles. So a cycle forms when a mapper is dependent on itself. So suppose user had a link to itself. So some user rows have to be inserted before others. Or if there's a cycle going through user to address to some object called widget that's then dependent on, the user's dependent on that, you might have to put some user rows in before other ones. You have to do inter-row dependency sorting. So we take the dependency graph that we've made and we break out just the parts that we need to into per object sorts. And these days, Guido has a function on his blog called cycle detection, and it was really neat, and I use it. It's in our source code pretty much verbatim. And the rationale of having these 2 topological sorts, where first we sort by mappers, then we look for cycles, then we do another sort, is because in the simple case, we don't have cycles, and it's way, way faster to just sort 2 mappers rather than all of the objects within each bucket. So when we have a partial ordering like this, where the user has a user.contact, that's a cycle, meaning some user rows have to be inserted before the other ones that reference the parent user via the contact relationship. So we break that up into this, where the user bucket breaks up into individual elements that are then put into the partial ordering. The address bucket stays as per mapper, and so suppose there are 2 user objects, one's dependent on the other, they both get put into the partial ordering as the address is dependent on both of those, and then the user object number 2 is dependent on user object number 1. So when we have this and we want to flush it, we get more of this kind of thing where we have the same address bucket, the same user to address bucket, but the bucket on the top is split up. So that's the cycle resolution. So if we still have 10,000 users, 10,000 addresses, we have 10,000 of these now, or maybe, actually they do get batched within the sort, but there'd be more buckets, but we still have the one coarse grained bucket here. And that is the theory of operation of the unit of work. That's how it works. And that is all the slides. So I hope this is a line now. So what's up? Anyone questions or?
I have a question. Would it be trivial to integrate SQLAlchemy or something like memcache to cache it?
So yeah. So I had a job a couple of years ago at a social media site where we needed to cache. So we actually have a whole example in the examples folder of how to integrate SQLAlchemy with the Beaker caching system, which is another tool that I was largely involved with. And you can integrate actually with any I'm actually kind of thinking of rewriting something to supersede Beaker. But yeah, we have a caching solution. It's not a feature within the ORM because when you use caching of queries in memcache, it gets really, really complicated really fast. And I need people to know exactly what they're doing. So we have it as an example, meaning you read all the code. It's only a couple of modules. Read it, understand what it does, and then you can do caching. And actually, the company LolApps did a talk at PyCon a couple years ago, and they were actually doing this. They weren't using my example, but they were already caching the result of queries in memcached. And so when I did the Beaker example, I added some elements to SQLAlchemy to make it easy to resuscitate objects from a cache, and SQLAlchemy objects are pickable. So the answer is yes, it's possible. And I did at least one website that's in production using a lot of Memcached. But it's really hard because it gets really complicated really fast because you're not sure who's coming from where, and it's hard. It's and validation, yeah. I mean, I found the best if you can just deal with very static data and you're totally happy with it just going stale after 2 hours. That's the best. If you have to actually, someone clicks a button, it's going to change, and it's got to you have you right through. Pain. So it can be done. I think Beaker has kind of had its day, and I want to do a better system that's more rudimental that would allow people to build patterns like that. Yeah. Hey.
I find that I can either sort of think in relational database tables or I can think in terms of objects.
Sure.
And it sounds from this like starting with the table, sort of thinking from there, and then building out would be the approach used for SQL.
Well, right. So SQLAlchemy is designed for people where I mean, every app I've built is like, let's design the database first, and that's really what you do. And there's kind of this thing where, oh, SQLAlchemy is for legacy databases. And what they're saying is that legacy database means that it's a schema that can't be molded to fit what the tool wants. And SQLAlchemy doesn't believe in that. We don't think you should model your schema to fit the tool. The tool should fit the schema. So I don't say that SQLAlchemy is for legacy schemas. I say it's for really good schemas. It's the schema that you want to build, and this is exactly how we want to do our data. And what's the tool that can work most effectively, and we try to make the ORM such that it can pretty much accommodate what you're doing. And of course, it works the best if you're using good relational patterns. If you've got a lot of denormalized stuff, then it's going to be more pain. The more denormalized you get, the more painful SQLAlchemy will get too, which you'd expect. So yeah, it is schema. You do think of turn the schema first, but I mean, I think of both at the same time now. So maybe that's yeah. What's next? Well, yeah, I mean, I think the bigger caching thing is what I've been thinking about lately. There is, what kind of tickets do we have right now? I mean, I want to get SQLAlchemy to get more adoption. I want to get it, I mean, I'm thinking about it just getting just a higher level of adoption right now. Some things I've thought about, there's two things I've thought about. I've thought about if you do have a non-relational database like a MongoDB or a Cassandra, and you also had a relational database, how can SQLAlchemy help you to integrate those two things? So there is a ticket in track where I have kind of an idea for how there could be MongoDB layers integrated with the unit of work. So that whole dependency thing, you'd be able to write a module that, like one of those buckets would actually persist to MongoDB or to Cassandra. So there would be ways that you could first insert the data in your relational database, and then your MongoDB would happen. It wouldn't do the querying side. So that's one thing I've thought of. The other thing I think of sometimes is people come to me with a stored procedure model, and stored procedures are a totally different way of thinking, and I have sometimes wondered if there would be a way for SQLAlchemy to work with shops that really want to do things by stored procedures, like either a stored procedure generation system, or maybe the way Postgres allows you to have Python stored procedures. Maybe there's a way to use part of SQLAlchemy within a Python stored procedure. I don't know that that's next, but I think about it. I don't know that I would have time to work on that, but those are things I think about that might, as far as big things, In the little sense, I'm just trying to get declarative to be completely kick-ass and get people's apps to be really easy to write and have a lot of documentation. Oh, and also there's a book project that I've never had time to do. I mean, there's a book we're supposed to be writing that someday there'll be a great book. I have, yeah. Is that it? All right. Thanks for coming.